Okay, in this experiment, we are going to measure the viscous coefficient of a liquid. Using this equation, this is the Poiseuille's equation. Poiseuille's equation is used to measure the volume flow rate of a viscous fluid through a pipe. This V over T, volume over time, that is the volume flow rate through the pipe. And delta P is the pressure difference at the ends of the pipe. R is the internal radius of the pipe. Eta is the viscous coefficient of the liquid, which we are going to measure here. And this L is the length of the pipe. So if we can measure these quantities except eta, we can calculate a value for the coefficient, viscous coefficient of the liquid. So for this one, we need this experimental setup. As you can see here, this is a constant pressure apparatus. So using this one, we can maintain a constant pressure head to the tube as shown here. This is a capillary tube, and this is a 100 milliliter measuring cylinder. First, we have to prepare, before attaching all these, we have to prepare this capillary tube. Since the viscosity of a liquid is highly dependent on the cleanliness of the tube or the container, we have to clean this capillary tube very well. So, using before attaching all these, we have to get this capillary tube, which is about 25 centimeter in length. So in order to clean this capillary tube, first we need to wash the inside of the capillary tube with sodium hydroxide. So we have to use a base first in order to clean this. Then using a diluted hydrochloric, which is an acid, again you have to wash it. And finally, using well water, you have to clean the pipe again. So we can make sure that the pipe is cleaned really well now. Okay, once the capillary tube is clean, we have to connect the capillary tube into the constant pressure apparatus. As you can see here, these are some rubber tubes. These are rubber tubes. Then attach this capillary tube to a stand, and then you have to make sure that the capillary tube is perfectly horizontal. We can make it horizontal by using a spirit level. Okay, then you have to attach a cotton thread to the end of this capillary tube. So now there's this constant pressure apparatus and the capillary tube. So once these two are connected, still we haven't included this measuring cylinder here. For now, this is a constant pressure apparatus and the capillary tube. So once this capillary tube is clean, then horizontal, and there's a cotton thread added to the end, then you have to open the tap which is connected to the constant pressure apparatus. So now the water will be filled into this constant pressure apparatus. So once the water filled to this level, the excess water will leave through this pipe to outside. Then so the water level won't exceed this level. So this constant pressure apparatus can hold a constant pressure head provided to the capillary tube. So after a while, you will notice that there is a slow trickle of water pouring through this cotton thread. So once it is steady, this will be steady because there is a constant pressure head. So once the trickle of water is steady, you have to place this measuring cylinder under here. Then you can collect water into this measuring cylinder. Simultaneously, you have to use a stopwatch. You have to start the stopwatch once the water starts to fill into this measuring cylinder. So you have to collect water into this measuring cylinder for about 3 minutes. Which you can measure using the stop clock. So once that is filled for about 3 minutes, you have to take the volume reading from here. Now you have a volume reading and a time elapsed. So using these two, we can find the volume flow rate. Once you divide volume by time, you can find the volume flow rate of the liquid through the capillary tube. Now we have measured this term, which is the volume flow rate. Okay, now we know how to find the volume flow rate through the pipe. Then let's consider how to find the pressure difference of the pipe, that is delta P. In order to find that, let's say that the atmospheric pressure is P naught. So atmospheric pressure is P naught. So the pressure above the water level would be P naught. And the pressure here also is P naught. That is outside of the apparatus, so this atmospheric pressure. Then let's say we need to find pressure here. That is the this end of the pipe, left end of the pipe. So that pressure should be P naught plus H rho G. H rho G is the pressure head. So this is P naught plus H rho G. H rho G, hydrostatic pressure caused by this liquid level. Then delta P is pressure difference between the ends of the pipe. So the pressure here is P naught plus H rho G. Pressure here is P naught. Then you have to get the difference of those pressures. So the delta P is P naught plus H rho G minus P naught. So the delta P is equal to H rho G. Then you just have to substitute H rho G instead of delta P here. Then you can measure the simple H value, that is the height to the water level from the capillary tube. You can use simply a meter ruler to measure the simple H. Then we know all these values are V over T, that is the volume flow rate. Simple H, we just measured that value. Then this rho, that is the density of water, we already know that. Then this is the gravitational acceleration, we know that as well. Then we need to find this internal radius of the capillary tube and the length of the capillary tube. We can easily measure these two as well. So once we know all those values, the only term we don't know in the equation is eta, that is the viscous coefficient. After substituting all the other values, and doing a simple calculation, we can find viscous coefficient. So that is one way to do it. But the accuracy of that method is much low. So we are going to use a graphical method in order to find eta. Here we are going to change the pressure head. We can change the elevation of the constant pressure apparatus. By changing that, we can change simple H. So that simple H is the variable that we are going to change. So we can call that the independent variable X. So when we change simple H, what changes is the volume flow rate. Since the pressure difference increases, the volume flow rate also increases. Then this whole thing, that is the volume flow rate, can be considered as the y variable which is the dependent variable. Then we are going to take a bunch of readings for simple H and volume flow rate V over T. Using those readings, about 6 readings, using those readings we can draw a graph